Hey everybody, Mr. McLennan here. So this video is going to cover the second part of 9.1, which we started last week. I decided to break it into two separate parts here. So this part we're talking about we're continuing on with their conditional statements. So before we go further, let's go ahead and just kind of quickly review what we mean by these conditional statements. So a conditional statement is if we break it into two separate parts here. We of course have a if P, then Q part. And if you remember, P represented the hypothesis. So that's what we are assuming. And then Q is equal to the conclusion. So when we're looking at it symbolically, we can look at it at if the hypothesis implies to the conclusion. So if the hypothesis, then the conclusion. So that's kind of how we started out with our conditional statements here. And then we talked about how other ways we could write the statements. So one way would be if with the converse. So the converse is if you kind of switch your conclusion and your hypothesis there. So instead of saying if the hypothesis, then the conclusion, we're going to try to rewrite it as if conclusion, then the hypothesis. So that is when you're doing the converse. The inverse is when you do the negate to both sides, to both your hypothesis and your conclusion. So this is going to tell you that if not the hypothesis, then not the conclusion. And then finally, we talked about the contrapositive. So contrapositive is kind of when you take the converse and the inverse at the same time. So you are rewriting it, the order. So you're going to put the conclusion first, then you're going to put in the hypothesis at the end, and then you're going to go through and you're going to negate both of them. So if not the conclusion, then not the hypothesis. So that's what we were talking about last time, and we're going to continue that conversation here today. So first thing we can do is that we can start looking at definitions. So you can write a definition as a conditional statement in if-then form, or you can write it as its converse. Both the conditional statement and its converse are true for definitions. For example, recall the definition of a perpendicular lines. So if two lines intersect to form a right angle, then they are perpendicular lines. You can also write the definition using the converse. You can also, let me say that one more time. You can also write the definition using the converse. So if two lines are perpendicular lines, then they intersect to form a right angle. So we took the hypothesis here. So the hypothesis is two lines intersecting to form a right angle. We grab a different color for conclusion. Then the conclusion is they are perpendicular lines. Well, let's see what happened to my red there. We'll fix that. Red back there. There we go. So that means that we're doing the converse of it, we're switching the order of it. So if two lines are perpendicular lines, so that's a conclusion, then our hypothesis was then they intersect to form a right angle. So we switch the order there when we're talking about the converse. Now, if it's true that both the conditional statement and the converse are equal to each other, you can then go ahead and write it as a statement. So you can say, for example, here, if we're looking at the picture at the right, when L and M are in fact perpendicular to each other because they have this 90-degree angle right here, we can then write it as line L is perpendicular to line M. And we can do it symbolically like that. So let's look at a couple examples, or at least one example here of this. So we want to look at the statements that are listed here for the figure on the right, and we want to decide whether that the statement about the diagram is true. And we want to explain using our definitions that we have learned in the past. So the first one for A we look at, it's saying that line AC is perpendicular to line BC. So if we're looking at that, we want to conclude, is that in fact true? And it turns out that it is actually true. So this statement is true because we have, well, the right angle. So we know that when two lines intersect and they form a right angle here, that means that they are in fact perpendicular. So you can say that the lines are perpendicular to each other. Let's look at B. So B says angle AEB and angle CEB are linear pairs. So if we go ahead and grab different color here. So AEB, AEB, and we look at lines CEB. So CEB, and they're saying if they are linear pairs. And it turns out that the statement is true. They are, in fact, linear pairs. By definition, if a non-common side of adjacent angles are opposite rays, then the angles are a linear pair. So because AE and EC are opposite rays, that means that angle AEB and angle CEB are, in fact, linear pairs. Okay. Now for C, ray EA and ray EB are opposite rays. So let's go ahead and let's kind of map that out. Let's go for our purple. I'm going to go purple for this one. So we're looking at ray EA. So EA. And we're looking at ray EB. So EB is this direction right here. And they want to say that they are opposite rays. And it turns out, though, that they are not opposite rays. This is actually a false statement. So point E does not lie on the same line as A and B does. So A and B are not on the same line. So because they're not on the same line, they are in fact not opposite rays. So for this to be true, EA would have to be an opposite ray with EC. So E does fall on the same line as A and C do. So that would then make them opposite rays. So they have to be in opposite directions. All right. Now I have the figure right here, and what I want you guys to do is use the diagram and decide whether the statements are in fact true. So I want you to just go through these and just figure out if they are in fact true or not. Okay, so hopefully you have time to go through those. Let's go through each of these and see if they are in fact true. So the first one is talking about angles JMF and angles FMG, and we want to know if they are in fact supplementary angles. So it might be useful if we talk about what the definition of a supplementary angle is. So let's identify. So we get JMF right here. I don't know why the pen keeps doing that. So angle right here. JMF. And then we have the angle of FMG. So FMG, FMG right here. So this angle here would be angle FMG. So for those angles to be supplementary angles, so the definition of supplementary angles is that the two angles must be adjacent to each other, which they are, as we can see, and that the angles, so angles JMF plus angles FMG would have to equal 180 degrees. That is the definition of a supplementary angle. And they are both adjacent. And it turns out that they are both add up together to be 180 degrees because this is if we look on the other side, so if I was looking at JMG, so angles JMG, that is in fact a straight angle. And a straight angle is equal to 180 degrees as well. So because JMF and angles FMG lie on angles JMG, we would say that that is in fact a true statement. So both JMF and FMG are linear pairs to each other, thus they are supplementary of each other. They add up to 180 degrees. All right, number 7. Point M is the midpoint of line segment FH. So let's go ahead and mark that. So point M is right here. Well, is that in fact the midpoint? Well, we can't say that's the midpoint actually. We don't know that because we're not provided information which tells us that is true. We would need to know that line segment FM would be equal to line segment MH. Now, if that was true, so let me go ahead and grab a different color here. If I knew that FM, so that's this line right here, and so we'll do that, so FM, and if I look at MH right there, MH. Now, if they were told that those two were equal to each other, then we could in fact say that they are in fact, or point M is in fact the midpoint. But because we're not provided that, then we cannot say that this is in fact true. So we have to say that this is a false statement. All right, we can look at number 8. So this is saying that angles JMF and angles HMG are vertical angles. So if we look at this, let me go ahead and fix that real fast. Here we go. So if I'm looking at this, let me get my pen back up here. Here we are. JMF. And we are looking at angles HMG here. So both of these end up having the same vertex right there at point M. And notice that they are on the opposite sides of two line segments being intersected there. So because they are on opposite sides, this turns out to be a true statement. So they are, in fact, opposite angles formed. And a quick note that vertical angles, so these angles right here, are in fact equal to each other. Those are in fact the same size. And finally, we're asked that line FH is perpendicular to line JG. Well, JG and FH do meet at point M, but we are not provided that information that they are in fact perpendicular angles. We are missing a piece of information to tell us that. If, for example, we were told that there's a right angle right there, so it'd be kind of like, let me go ahead and fix that, make that look a little better. So this would be a more of a flatter side there, and then this would go more like that. It's kind of hard. You got to think of it three-dimensionally to visualize it, but the right angle would look something like that there. But it turns out that because we do not have that right angle, it's not provided to us, we cannot say that that statement is in fact true, so we have to consider that being a false statement there. All right. Now what we're going to do is we're going to look at the writing a biconditional statement. So a biconditional statement is when a conditional statement and its converse are both true. So you can write them both as a single biconditional statement. This statement contains both the phrases if and only if in it as well. If only if it's true that the conditional statement and its converse are in fact true. So we're going to be able to look at an example of this. So we want to write the definition of a perpendicular line as a single biconditional statement. So by definition, if two lines intersect to form a right angle, then they are perpendicular lines. So if we're going through this, first the solution we want to do is we want to let P, so remember P is the hypothesis, be that two lines intersect to form a right angle. And we're going to let Q be they are perpendicular lines. So we want to use red to identify the hypothesis, and we want to use blue to identify the conclusion. So we're going to write the definition first as the conditional statement, so kind of how it was written above here. Let's go ahead and just quickly identify them. So remember, we're going to have in red B for the hypothesis. So if two lines intersect to form a right angle, and then our conclusion is that they are perpendicular lines. So if we go down here, if two lines form a right angle, then they are perpendicular lines. So we highlighted the correct thing, the same thing as they had down here. Well, that is the conditional statement, but we can write it as the converse. So notice that we switched the conclusion and the hypothesis here. So now it says if two lines are perpendicular lines, then they intersect to form a right angle. And if both of those are true, then we can write it as an if and only if statement. So we can use the definition and its converse to write the biconditional statement. So now we can write it as two lines intersect to form a right angle if and only if they are perpendicular lines. So because it's true both ways, we can go ahead and include this if and only if statement in there. If it wasn't true the other way, then we could not go and include that there. All right, so now I have two problems here I need you to look at. I want you to rewrite the definition of a right angle as a single biconditional statement. And then for number 11, I want you to rewrite the definition of congruent segments as a single biconditional statement. So first thing, remember what you want to do is you want to identify what is your hypothesis and then what is your conclusion there. So let's just say for number 10, we were looking at this. If an angle is a right angle, so that's the hypothesis, then its measure is 90 degrees. So its measure is 90 degrees would be the conclusion. If I was looking at the second one, so if two line segments have the same length. So two line segments have the same length, that is the hypothesis, and then the conclusion is then they are congruent segments. So what I'd like you guys to do again is to go ahead and rewrite both of those definitions as a single biconditional statement. All right, hopefully you had an opportunity to do that. And we're going to go through and take a look at these. So if we're looking at the right angle here, so of course the definition that we started out with, if an angle is a right angle, then measure is 90 degrees. We can go and write it as the converse. So the converse would be, of course, if we flip them around. So if an angle measure is 90 degrees, then it's a right angle. And if both of those are true, then we can write it as the if and only if within our single biconditional statement. So our biconditional statement would be an angle is a right angle if and only if it measures is 90 degrees. All right. Number 11, we can go through and do this. Again, we already identified what the hypothesis and the conclusion were for both of these. So if two line segments have the same length, they are congruent segments. So if we want to do the converse of this statement, that would be if two line segments are congruent segments, then they have the same length. So again, we just swapped around the hypothesis and conclusion there. And because both of those are in fact true, we can write it as a biconditional statement with including if and only if in there. So two line segments are the same length if and only if they are congruent segments. So that's how you're able to go and write a biconditional statement from these.